Ready, set. Welcome,
Hey,
everyone.
Hey,
what's up,
pre-cal.
pre-cal? What's up? What's up? What's up? What's up?
All right, we are back for more sequences and series.
So to start us off, I am going to start with the top of the notes. So let me present my screen. Okay. All right. Okay, let's make this big. I know last time it was like small for a long time. My bad. So let me just zoom in some. All right. Yes, there we go. So to begin, geometric sequences, it's a little bit different than arithmetic. Arithmetic is where you're adding, and geometric sequences essentially is where you're multiplying. That's like just a shortcut version. But we have this definition, a pattern where the ratio of consecutive terms is always the same, and it's not adding pattern, it's ratio. So with ratio, that's dealing with like fractions, which essentially a fraction is dividing or multiplying by the reciprocal. So it's got to be a multiplication situation. So from 2 to 6, that's multiplying by 3. And so in order for this to be geometric, it has to be multiplying by 3 all the way through. So, yeah, that's times 3. 18 times 3 is 54. 54 times 3. Yes, all of those multiply by 3. So just seeing that 2 to 6 is times by 3, I was able to multiply to figure out what happened. But you could also divide to figure out what happened. If you divide the second term by the first term and the third term by the second and the fourth by the third, so on, you end up getting 3 as the common ratio. So what
You're
does
pretty
that
much
mean?
dividing by the number in front, right?
Right, exactly. You literally just going to divide by the number in front. So you could do 6 divided by 2. So we're just going to go backwards. 6 divided by 2, or 18 divided by 6, or 54 divided by 18. Either way, you end up getting the answer is 3. And so that is what we consider our common ratio. Now, we need a general rule for this bad boy. Our general rule is going to be R equals, because R is our common ratio, versus with arithmetic, it was D was our common ratio. Why does it not start with like a C? I don't know. I guess ratio starts with R, different started with D, so that's why. So just remember that. The formula is A sub n plus 1. So then, in other words, that's the next term divided by A sub n, the previous term. It equals A sub n plus 2. So the next term divided by A sub n minus or plus 1. So the previous. Exactly what I just said. The second term divided by the first, the third divided by the second, or the number in front. All right. Let's do some examples. Example numero uno. We are going to show that A sub n equals 2 to the negative n, and it has to be geometric. All right, you could do this the old school way and just plug in numbers like, okay, n is 1, so 2 to the negative 1, n is 2, 2 to the negative 2. Or we can do it algebraically, which is what we're going to do. We're solving this algebraically. So R equals A sub, what is that? A sub n plus 1. And where is that n plus 1 coming from? It's coming from the equation or the formula up there, divided by A sub n. And where is that sub n coming from? From this equation up here. So we want to plug it in and see if we indeed get a common ratio, or essentially what value we end up getting, and that is our common ratio. So let's figure it out. Now we want to use 2 to the negative n plus 1, and I'm going to put that in parentheses because I'm substituting n plus 1 in for n. And then I'm going to divide, and it's going to be 2 to the, or 2 sub, or 2 to the, yeah, definitely to the negative n And essentially, like you're putting it in parentheses again because I'm substituting in for n. And now we just got to simplify and solve. So we have 2 to the negative n minus 1 when we distribute the negative, divided by 2 to the negative n again when we distribute the negative. Since our bases are the same, then I literally only have to move my negative n exponent up, and then make sure when you move it up, the value of it changes as well. So if it was positive, it's going to turn negative. Now that it's negative, it's going to turn positive. And so we have common bases, and we can put all the exponents for the common bases with one base. So that's negative n minus 1 plus n. Dun, 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 dun. And then
you're kind of doing that because, like, if these were like back in math 1, when we were dividing, we just subtract the exponents. Is kind of like what another way to say what you just did. I think of it as subtracting the exponents.
So essentially, if you think of it as subtracting the exponent, it would have been minus a negative n. But when you have minus a negative, that's the same thing as adding, which is the moving it up part. So you can think of it as subtracting when you do laws of exponents, or you can think of it as, okay, common denominators or common bases. Oh, I just need to move my exponent up to the top. Subtracting is the mathematical way to do it, though. So we have these, and we end up with a final answer. Oh, well, when we see this is a negative n, that's a positive n, and we end up with 2 to the negative 1. Ta-da! And this like random parenthesis doesn't need to be there anymore. And so 2 to the negative 1 equals, oh, well, y'all know what 2 to the negative 1 power is. Again, using the law of exponents or the exponent rules, that means we're going to take our base and exponent, which is technically a 1, and then remove it to the denominator so that the exponent turns positive. And what's left on the top is a 1. You can't just leave it as nothing. And so that reduces or simplifies to be simply just 1/2. And so that is our R. And therefore, this is indeed geometric.
Because we have an R.
Because it's simplified, yes, correctly, to be an R, period. And you got a final answer, a numerical value. And that is it. Yay. Now, let's do example number 2. Okay, same situation. We want to show that this thing is indeed geometric. All right. Okay, let me see. Okay, here we go. So
I feel like this would be
R
a good time for them to pause and see if they can do it.
Yes, pause, see what it is, but R equals, don't forget, A sub n plus 1 over A sub n. And I'm just going to replace my n in my equation or my expression with n plus 1 and regular n. So yes, at this time, go ahead and pause it. Pause it, see if you can get the right answer. If not, I'm continuing. If you paused, welcome back. Hey, how you doing? So let's keep on going. So this is negative 3 times 1/4 to the n plus 1. And remember, I got that from putting n plus 1 on top. And then negative 3 times 1/4 to the n. And remember, I got that from putting, oh, don't do that. Don't scribble it out. For putting n on the bottom. And then we're going to do it the same way we just did example number 1. We're going to simplify. So this is negative 3 to the technically 1/4 n plus 1. Oh, do I want a plus 1? Yeah, I do want a plus 1. And that doesn't like simplify at all. And then all over negative 3. I guess I could just solve it and simplify it first. So before I do all of that and like rewrite the same thing all over again, we are going to go ahead and clean this up now that it's written. So unlike the one before, we didn't need to distribute. It's going to stay with the 1/4. 1/4 will still have to the n plus 1. The only thing I could do differently is get rid of the parentheses, but I don't want to do that because the 4 is going to the n plus 1 as well. So no need to rewrite. Let's go ahead and cancel. See if we can simplify, clean this up. Negative 3 and negative 3, that goes away. Ta-da! And you end up with 1/4 to the n plus 1. And then you end up with 1/4 to the n. Well, we're doing the exact same thing. Remember, as before, you have common bases, or you can think of it as subtracting, and it ends up being 1/4 to the, and then this is n plus 1 minus n. And this time we don't need an additional set of parentheses because we have a positive n minus a positive n. And then we can clean it up. N minus n leaves us with, I don't know what I was about to say, 1/4 to the first power, and 1/4 to the first power is just 1/4. And that's our R. Again, because we ended with a value, a numerical value, this again is geometric. Ta-da!
I wonder what it would look like if it wasn't. Like, what would happen? Like, would there still be like ends left or something? Like,
I guess so. If it didn't end up with just a single number, fraction or whole number, and it ended up with variables still, then you couldn't say it was geometric because you can't times by the same thing every time if you're left with a variable, because variables can represent any number. So you can't have a variable ratio. It has to be one specific numerical value.
gotcha. Makes sense.
And that's it. All right. Last little section for my part is finding a rule. Okay, so here's the rule, the formula. A sub n equals, and we always do brackets, A sub n, nope, A sub 1, sorry, times R to the n minus 1. And it seems like a difficult equation, or maybe not, formula, but it's fairly simple. This is the rule that we're going to use to find the, to essentially create a rule when we're doing geometric sequences. So let's figure out what A sub 1 is first. A sub 1 is the first number in the sequence, and that is 2. And now we have to figure out what in the world is R. So this one we did already, but remember, you can always just take the number divided by the first number, or the number divided by the previous, whichever number you choose. So you could have chose 162 divided by 54, or you can think of it as, well, what times 2 is 6. Regardless, both of these should give you the same number, which is 3. And so our rule is A sub n equals, we put the brackets just like the rule says. A sub 1 is 2, and then we're going to times it by our R, 3 to the, and I'm going to put it in parentheses, well, the 3, negative, or n minus 1 power. And this is our rule. Ta-da!
So
All right.
is that going to work every time?
Every single time, like literally. So for example, if I wanted to figure out what, like, if I could use the rule to get 162, like that rule don't work. Well, this is 1, this is 2, like that's term number 1, that's term number 2, this is term number 3, this is term number 4, this is term number 5. So if this indeed works, we should be able to do A sub 5 equals 2, in which this particular one, we're finding one answer, so we don't need the brackets. So 2 times 3 to the 5 minus 1 power. And that is 2 times 3 to the 4th. And handy dandy calculator equals, that was me and my calculator, 162. Ta-da!
Yeah.
So it totally works every single time. And there's your sequence. Or there's your rule for this sequence. And Miss Willis is going to continue doing more examples. Let me stop sharing my screen, and it's her turn.
Hopefully, I can talk as fast as Miss Marshall. Make this video short.
Good luck.
I know. I'm not a fast talker. It's okay. All right. So she just finished. Let's see. Let me scroll. Find the 17th term. So we're on example 4. So I'm doing this next page. So again, if you're like, oh my gosh, these videos are too long, you can always pause it at our sections and then keep going later. Anyways, 17th term of the geometric sequence. So in order to find the 17th term, I need to find my rule. So I got to find be a sub n equals a sub 1 times r to the n minus 1. Okay, so one thing I do already know, I know what my first term is. So I know that a sub 1, the first term in the sequence is 2. So now I just got to find the common ratio, but there's a whole bunch of fractions. So I'm actually going to also use what Miss Marshall taught us, that if I wanted to find the common ratio, all I got to do is take this number and divide by the number in front. So 2/3 divided by 2, and you can type that in the calculator. I did bring up my calculator, but that equals 1/3. And it's a good habit to always check, like, does it work? I should get the same thing if I do 2/9 divided by 2/3. I should get the same thing if I do 2/27 divided by 2/9. Like, I should be getting 1/3. And if I'm not, then this sequence is not geometric. So always check. It's a good habit to do that. So what I'm doing here is I am multiplying by 1/3 each time. So now I can make my rule and then plug in the 17th term. So I can say, okay, they want me to find the 17th term. So my n is 17 when I plug into this rule right here, when I plug into my formula. So I have a to the 17th equals my a sub 1 is 2, because that's the first term, times, I want to make sure I put this in parentheses, especially since it's a fraction, 1/3 raised to the n minus 1. Well, my n is whatever's down here. So this right here is my n. So my n is 17, and 17 minus 1 we know is
16.
And then if I go to my calculator, like, let's just see what happens when I type this in. Times 1 divided by 3 raised to the 16. Ooh! What just happened there?
It's no bueno.
It's not good. No, it's not exact at all. So a way to get around this, because it's a big number. No, it's a small number, 0.0000, because of my scientific, it's going the other way. So to get around this, what I got to do is I got to break it up. Instead of typing it all in, I'm going to do, okay, well, that's 1 to the 16th over 3 to the 16th. According to my rules, that fraction gets that 16th. So then I can say 2, well, I know any power is 1. And then 3 to the 16th is a huge number, so this is why it's really small. It's 43 million, 46,721. And then to finish it up, now this is a thing that unfortunately happens a lot with you guys, is you like to try to multiply everything by 2, but really it's just the 2 is the numerator. So it's 2 over this number. And guess what? I bet if I type this in my calculator, it's going to give me that exact same crazy decimal. Isn't that wild? It's wild. All right. Number 5. So this one is giving me the A1. So they already told me that. They've given me the R. Oh, this one's so easy. This is a plug and chugger. So you have 8. So I'm going to use that green highlighted formula, the same one from the previous problem. It's a good idea to maybe pause the video, see if you can do it. They want me to find the 15th term. So that equals A sub 1, which is 2, times my R, which is 3. But when I plug in 15, because 15 is my n down here, so the n's going up here. So 15 minus 1 is 14. So only the 3 is getting the 14. And don't be PEMDAS. Don't forget PEMDAS. You don't do 2 times 3 if you're going to break it down. A lot of you guys break it down. Just type in your calculator. This number is 9,565,938. Woo! These are big numbers. Big numbers, because guess what? Geometric sequences, if you were to make a function, they're exponential functions, so they increase rapidly. All right, here we are. they want the explicit rule and the recursive rule. So explicit is what we were doing. So explicit is where we need to find a sub 1 and we need to find the common ratio. So a sub 1, the first term is 2. To get my common ratio, I'm going to do 8 divided by 2, which equals 4. And again, just checking, does 8 times 4 equal 32? Yes. So it looks like it kind of works, at least for the first two. So my explicit rule is just plugging in without any numbers. So it's a sub n, without any n's, there is numbers. A sub n equals, I'm going to use my little bracket, 2 times my common ratio, which is 4 raised to the n minus 1. And that is the explicit rule. That's the rule I can do if I want to find any term. Now they want the recursive rule. And so the way, again, last video we talked about recursive rule. It can be written 2 different ways. So, but the thing that it always has to have is your starting term. So you have to say, okay, a sub 1 equals 2. Then you write a rule. So I say a sub n equals a sub n minus 1 times my common ratio, which is 4. So this is like your next now. This is not, this is just showing you the pattern. This is not where you would plug and chug. What is the 4,000th term? If I wanted to know what the 4,000th term is, I would use my explicit rule. Yep. And that's how you do explicit and recursive. All right, last one on my page. Identify whether the following sequence are arithmetic, geometric, or neither. If it's arithmetic, find the common difference. If it's geometric, find the common ratio. So I always check arithmetic first. So you, just like we were doing the second number divided by the first, if you're wanting to find if it's arithmetic, you do the second number minus the first. So 10 minus 4.
6.
Yeah, looks like I'm adding 6. Well, if I added 6 here, unfortunately, I don't get 18. So it's definitely not arithmetic. So I'm going to check geo. So I'm going to do 10 divided by 4. That gives me 2.5. And then if I do 18 divided by 10, ooh, that's not the same common ratio. So this is
Neither.
neither. Good. So that one's neither. Ooh.
This would be a good time to pause it. Try. See if you can do B, C, and D.
Because it's pretty easy, I think. Honestly, this one kind of looks, to me, it kind of looks like geometric. Just because, like, how can I start off, like, with a really big number? So if I went from 600 to 100, that means I would be subtracting 500. It doesn't look like I'm subtracting 500 each time. So it's not arithmetic. Does look, though, like I'm multiplying by something. So I'm just going to check. What is...
Those are all powers of 5.
Yeah, they are. But I like to check. I think I know that this one might be geo. So it looks like it's might be multiplying by 0.2. So I could also, though, so what I did is I did 125 divided by the number in front. And you can
even though it's smaller, it's still the second number.
Yep. Always starting with the number behind. So then 25 divided by 125 looks like it's 0.2. I bet if I did 5 divided by 25, it would still be 0.2. So that means that this is being multiplied by 0.2, or if you really want to, you could hit math frac and say we're multiplying by 1/5. I bet you were probably like, oh, I'm dividing by 5. No, you don't ever want to say you're dividing by 5. Geometric is straight multiplication. Arithmetic is straight adding. You can add a negative and you can multiply by a fraction, but that's what the pattern is, adding and multiplication. So this one is geo, and so my common ratio is 1/5, not divide by 5. That would be 100% wrong, I think. All right. At least I would count it 100% wrong if I was, doing this. I'm gonna look at this one's really easy actually. I think I know this one without my calculator. Looks like kind of just like B. I'm
Powers
getting
of 9. Powers of 3.
powers of 3. Okay, so it looks like I'm dividing by 3, but like I just said, I can't divide by 3. So I'm
1/3.
yes, multiply by 1/3. And if you're not seeing that, just check it in your calculator. Second number divided by the first number. Third number divided by the second number. So R equals 1/3 because 3, and it still works. You always want to check that last one. 3 times 1/3 is definitely 1. All right, last one. This one looks crazy. I know that 1 plus 1 gives me 2, but 2 plus 1 is not 6. So it's not arithmetic. I know that 1 times 2 is 2, but 2 times 2 is not 6. So it's not GO. So then this one is
Neither.
neither.
Oh,
Woo woo. Hopefully that made some sense, my friends. Here goes fish.
All righty. Big times. Big times on the horizon. Okay, so just like we did with arithmetic, we are going to learn how to add a certain number of terms for our geometric sequence. And there's going to be 2 ways you can do that. One way is going to be with a formula, and the other way is going to be in the calculator. So we're going to start with our formula. So starting with S sub n, and again, the S stands for sum, and the N stands for the number of terms you have. It's going to equal A1, then parentheses 1 minus R to the N power all over 1 minus R.
and y'all see how I'm paying attention? Miss Fisher has me on the screen still. Y'all should be paying attention as well.
Oh, I'm sorry. Do you want me to take you off the screen? Yeah.
Or make it bigger. I know I had a kid tell me last time it was too small because I forgot to like make my screen big. It's like, oops, my bad.
I
If
left
I was
that.
on the screen, I was definitely on my phone. So whoopsie.
I left that space for my calculator for in a second, and I'm used to doing that for my Google Meet, so I can still see the chat.
I just
So
hope it's still there.
I'm sorry to make you uncomfortable.
I don't know. They just saw me paying attention, and I needed them to see like this what it looks like to be a studious student.
All right. So this first question says, find the general sum. So when it says S sub n, n is in general terms. And if you look at this problem right here, they don't really tell us where it ends. It ends with a term that still has n in it. So this is going to still be in general terms. So the way that that's going to look is we are going to substitute in everything that we possibly can. So according to the sum formula, we need a sub 1, which is the first term. We need 1, and we need R. N stands for the number of terms you're adding up, but that is an unknown to us. So our answer is still going to have N in it. So our sum for N number of terms is going to be 1/4, and then times 1 minus R to the N power, and then 1 minus R. So I need to know what R is. So off to the side here, I'm going to take term 2 divided by term 1. So 2/4 divided by 1/4. And note, they didn't reduce these terms. Like I know that 2/4 is a half, but there's a reason that they did not simplify that for us. And that's just to help us see that there is a pattern going on here. It's a lot easier to see the pattern when it's 1/4, 2/4, 4/4, 8/4. And note, they didn't even simplify it to 8 and to the 4 here. They left it in terms of an exponent, so you can see it's a geometric pattern. So to simplify this for R, we're going to just cancel out these 4s here and get that the R value is 2. And you can also see that with the powers of 2 that are happening there in the numerators. So the R value is 2. So this is going to be 2 to the N power over 2 in the denominator. And then you're going to want to clean that up as best you can. So in the denominator here, 1 minus 2 is going to give you a negative 1. You're going to multiply that by the 4. And in the numerator, you're going to multiply by the 1 on the outside. So you're going to have just 1 minus 2 to the n power. And in the denominator, you're going to have a negative 4. And that's about as best you can do. So that is a general sum for that geometric sequence.
I can't divide 2 and 4. Why can't I divide 2 and 4?
Oh, you cannot divide and simplify anything unless it's a multiplication problem on top, Miss Willis.
You're right. You're right.
Or I guess if the 1 had a 2, like, could be divided as well.
Yeah, all 3 terms would have to be divisible by the same number.
But what about that little n up there with that exponent? Is that going to affect anything if we're all 2s?
Yeah, that also comes into play with the fact that you can't simplify something that has an exponent with something that doesn't have an exponent. They would have to have the same bases. Which
So this is
4 does. You can rewrite 4 as 2 to a power, but then due to the fact that it is part of a subtraction problem, you cannot simplify it either.
Okay, so it's as good as it gets.
Right. We're done.
You guys are just making complicated questions now. You're just trying to test me on a Friday. All right. So for number 9, find the sum. This is one we actually know where this one is ending. It's ending on the 14th term, and we know that, just kidding. I'm lying. This was a trick question. If you look, number 8 and 9 are actually directly related. They're following the same pattern, and they gave us this question as a follow-up because they want you to see the pattern and that it's a geometric sequence. So if you look, you've got 1/4, 2/4, 2 to the second over 4, 2 to the third over 4, and so on. This second term is 2 to the first, but it's the second term, right? So when we get to 2 to the 14th, it's not the 14th term. That's actually the 15th term.
Because of that n minus 1.
Right.
Yeah,
that's an n minus 1. So at this spot, n is actually equal to 15.
That makes sense.
Okay, so we've already been through the sum formula in number 8. So the intention there in finding the general sum formula there is that we can now just substitute in 15 into that sum formula. So we're finding the sum of the first 15 terms. We can just substitute in 1 minus 2 to the 15th all over negative 4. So if you just take your handy dandy little calculator and just type in 1 minus 2 to the 15th, and 2 to the 15th is going to be a ridiculous number, like you saw with the problem that Miss Willis did. You're going to get a big number, and then you're going to divide it by negative 4. The fact that this number is not in the denominator, though, the 2 to the 15th, your calculator can handle it a little bit better. So we get 8,191.75. Okay. All right, so that's one way you can find the geometric sums. The other way is that you can figure out what the equation is and use the sigma notation and use that feature in your calculator. So we're going from term 1 to term 15. And the formula is 2 to the n minus 1 over 4. So that was also kind of given to us as a hint in example 8. By leaving that as a general last term, they were giving you the equation for the sequence. So you can use that feature that that's in the calculator that Miss Willis showed us last week. So go to the math button and go down to the sigma notation option.
And if you have the old one, you're going to have to do all of the other stuff.
All those other steps. So
it might be good to know the general sum equation.
Yeah. All right, so let's talk about something that's called geometric series. So this geometric series which is also known as a converging series, is where we have this strange concept of adding up a series that gets infinitely smaller. So that happens when your R value is a number that's between 0 and 1. So if your R value is like a third. So it's a bizarre concept. It's a geometric sequence that never ends. So if you look down to this notation, you would have a sum that goes to infinity. And the other part is that your R value has to be between 0 and 1.
Can I just type that in my calculator? Is there an infinity button?
There's not an infinity button on your calculator. Maybe one day, Miss Willis, if you are motivated, you can program a calculator that will be able to handle that notation. But right now, if you try to ask your calculator to sum to infinity, it would never stop. And you would never be able to get an answer from it. So we need intelligent students to help our technology handle the concept of adding something forever.
But just to be clear, no infinity button.
No infinity button.
So I gotta do this by hand.
You have got to do this by hand. And I realize there's a little typo here.
Got it.
We have different variables going on our paper. Okay, so what is happening here is that we are going to ask you to add up and find a sum of something that goes on forever. And so that should feel mind-blowing for a second, but I'm going to try to explain to you why we can actually get an answer to this. So I want you to think about the sum formula that we just wrote above. And think about what happens if your R value is something small. I'm going to use a number like a half. And think about what happens as the n value gets closer to infinity. So let's say that we have our a value, and we have a number like a half. So we have a, we have a number like a half, and I'm asking you to sum to infinity. So the concept of raising something to infinity seems kind of strange. So I want you to think about what happens if we have this raised to like the 100th power. Okay. So first of all, in the denominator, let's talk about what is 1 minus a half in the denominator. So 1 minus a half gives us a half. Okay. All right. So up top, what we have is 1/2 raised to infinity, technically. So think about a number like 100. If I raise 1 to the 100th, what do you get?
1.
1. All right, no big deal. But if we raise 2 to the 100th, what are you going to get?
Something really big.
Something really big. Okay, so if you have something really, really big and you have 1 divided by a really, really, really big number, so 1 divided by something huge, what's going to happen is that this term right here becomes really, really close to 0. So you get 1
so it's like
divided by something huge approaches 0. So this is like the concept that we talked about at the very beginning of the year, like the idea of a limit.
Limits?
What? Okay, so what's going to happen is that this term right here becomes insignificant. So what ends up happening is that when n becomes infinity, when this goes to infinity, this whole term becomes insignificant. And so what you get is you get a sum to infinity really becomes this formula here, which really, if you multiply by a, becomes this formula here.
Beautiful.
All right, so these problems are really, really easy. to do, because all you do is you substitute into this lovely little formula that I just boxed in purple. So if I find the sum to infinity, and again, the concept's really weird, but if you think about the pattern, if your common ratio is a number between 0 and 1, every term in your sequence is getting progressively smaller. That's what the idea of a converging series is. It's all converging onto a single number, and that number is the sum that we are going to get. So we are going to add 1 plus a third plus a ninth plus the next number that would come in the sequence plus, and you're going to keep adding, okay, the next number that comes in the sequence. And so it's going to become more and more insignificant because these fractions keep getting smaller and smaller and smaller. So when you add them and add them and add them and add them, they become so insignificant that really your sum is going to be the number you get when you do this formula, A1 divided by 1 minus R. And so our R value here is going to be 1/3 because you're multiplying by a third every time. So sum to infinity is 1 over 1 minus a third, which is 1 over 2/3, which if you keep change flip, you get 3/2. So if you add up all of these fractions, you would get 1.5.
So I only use this formula for infinity, though. I can't use this
Only
formula
for infinity.
I can't use this formula for the first couple problems you did.
No, because those are getting huge. These are getting small.
Okay.
All right, so for this one, sum to infinity, and this dot, dot, dot shows you it's going to infinity. You're going to do A1 divided by 1 minus R. And here, the R, if we divide 4 by 8, 2 by 4, our R value is 1/2. So 8 divided by 1/2. Keep change flip, and you get 16.
And I would know that a sequence doesn't converge if I got like my R was 2 instead of 1/2.
Right. So a converging series is one where the numbers are getting progressively smaller.
And R has to be between 0 and 1. Like it has to be a fraction.
Yes. All right. So the last one, this one's written in sigma notation. Your key here is that you got the infinity on top.
But no infinity button.
There's no infinity button. Okay.
I mean, I could already see the students coming up to me during a test. Where's the infinity button?
Where's the infinity button? There is.
We went over that in class. Good luck.
All right. So here, the key to this one is that you have to pick out the A1 yourself. So you have to recognize that off to the right in your sigma notation, this is your formula. It's A1 times R to the n minus 1. So your A1 and your R are written here in the formula. So A1 is 2, and then it's 1 minus R. So you simplify, you get 2 over 1/3. Keep change flip. Your sum is 6.
Woo!
Yeah.
Yay! That was so much fun. I had so much fun. I always have
so much fun.
So that concludes our geometric secrets notes.
Conics are next. Get ready. Conics.
Prepare yourself emotionally.
I love conics.
Conics. All right.
Sorry.
Have a lovely, lovely week, everybody. And we'll see you in class.
See y'all. Peace out.